Good afternoon, Technation. Welcome to another Webinar Wednesday. Today's presentation is eligible for 0.1 CE credits from the ACI. Let's get started by giving away one of our Technation Tour t-shirts to the first attendee that can tell us which Pac-12 university was home to the Lawrence Brothers Radiation Laboratory, which is cited as the discovery of nuclear medicine. Answer now using the questions feature on your dashboard. I'll give you a hint. It's in California, and it's not the Bruins, and it's not the Trojans. While you're answering, let's remind everyone about our next stop on the Technation Tour. Is going to be the Spring MD Expo in Dallas, April 21 to 23. Our sponsor today, UMRI, has included a VIP pass in the webinar workbook, which will give complimentary entrance into our 3-day MD Expo. You can register by visiting mdexposhow.com. Okay, looks like some of the answers are coming in, and we're getting close. Oh, we got a winner here. Randall Antonucci, looks like. Congratulations, Randall. We'll get your t-shirt size and send you one of our great Technation Tour t-shirts. Okay, let's get started. Technation would like to thank Universal Medical Resources. Universal Medical offers the very best new and refurbished gamma cameras, quality parts, and repair services. In addition to these core products and services, Universal Medical rebuilds and replaces camera detectors, moves camera systems across town or the country, and supports our customers with expert in-house support. For more information, you need to visit uni-med.com. Our presenter today is Craig Diener, Senior Product Manager at Universal Medical. Craig has 22 years of experience in nuclear medicine, which includes 19 with an OEM in multiple capacities, including production technician, production management, system procurement, and asset management, as well as product management. Craig will be joined by Mike Hill, Chad Watson, and Kevin Bohr, Universal's panel of experts. Craig, you can begin whenever you are ready.
Thank you, John. Welcome, everyone, to our staving off end of life webinar. Once again, as John said, my name is Craig Diener, and I'm joined by the UMRI technical advisory staff here. So we've got a lot of material to cover, so let's look at the topics we'll be covering today. For those who attended the last webinar, we will review ways to protect your nuclear medicine system. We'll look at some tips and tricks for troubleshooting some common problems that are encountered in the field. We'll look at the most common part failures for 7 different cameras. We'll show you the benefits of using qualified reconditioned parts versus as-is parts. And then we'll have time for some of your questions at the end of the session. So starting with end of life, have you received an end of life or end of service letter from your OEM? If so, it's time to start planning. Is it time to purchase a new system? And if a new system is not in the budget, what can you do to continue the life of your existing system? Well, for starters, find out what the OEM's obligation is under the current contract. Usually it's a best effort support from the OEM. However, safety upgrades are the OEM's responsibility as long as the camera is in clinical use. An alternative is to find a good independent service organization or an ISO. ISOs are a viable alternative and can be found simply by searching on the internet or trade publications. Look for a company that has an extensive inventory of parts for your make and model of camera. Find a supplier that you can work with and trust. If possible, visit their facility and observe their parts testing and inventory process. Don't wait until the system fails to do the research. Many ISOs provide hands-on certified training for your internal clinical engineers as well. So let's review some of the topics from my last webinar on protecting your investment. Starting with extreme environmental conditions. This can have an impact on electronic components, especially if you live near the sea where high levels of salt and humidity are in the air. Proper shielding is important, whether purchasing a new system, relocating your current system, or just keeping your system in place and performing like new. Consider your hot lab placement. Improperly shielded sources can cause image quality problems. Be sure to put sources away when not in use. Be aware of injection locations and patient waiting areas. Injected patients walking to the restroom or other areas near your camera can create image problems. Make sure your camera is not getting interference from other nuclear medicine cameras, CTs, or MR systems. Power quality is very important. Power disturbances are prevalent everywhere in the country. Surges, brownouts, unstable power, and noise are extremely harmful without proper protection. This can lead to damage, lack of reliability, corrupt software files, downtime, lost revenue, and a lot of frustration within the department. A UPS is the best investment for your system to avoid these catastrophes. Preventive maintenance is an insurance policy against future downtime. Be sure to keep up with your image quality checks. You can often find problems before they become big problems just by doing your quality checks. Greasing and lubrication extends the life of critical mechanical parts. Removing old grease and applying new lubricant is a simple and cost-effective insurance for your camera. Fans are the most important part of your system and should always be inspected and replaced when needed to keep from overheating and component failure. Inspect critical stress points for cracks and fractures in your patient pallet. An occasional check of sensors and e-stops can avoid a patient fatality and reduce your liability. Establishing a regular routine of quality checks ensures your camera runs smoothly today and for many years to come. In the past, we've discussed the different types of service contracts. The 5 types to keep in mind are full service maintenance contracts, co-op first pass contracts for sites with in-house clinical engineering staffs, preventive maintenance only, cap coverage, and time and materials only. There are many choices, so be sure to pick the one that fits your needs and your budget. Be sure to back up your patient data on a regular basis. HIPAA and HITECH provide guidelines for patient data handling. Things that need to be considered when looking towards reconstruction of a failed hard drive are making a list of all software versions installed. This should include optional software packages that are installed on the computer, such as 3D reconstruction software, printer software, and DICOM. Be sure to note not only the optional software that's installed, but its current revision. Archive specialized or unique software configurations if possible, network configurations, current imaging corrections, and motion information if applicable. Consider investing in an archive solution such as critical product recovery to minimize your downtime in the event of a hard drive failure. So let's look at some of the most common spec problems that may come up throughout the course of your work week. I mentioned environmental conditions earlier in the presentation, and I cannot stress this enough. These are some of the steps to take in detecting these problems. Checking the quality of the power is one of the first things you should do when troubleshooting problems such as image quality issues or intermittent problems. Room temperature above OEM specifications can cause component failure and in some cases void your warranty. Background radiation can cause problems while scanning, but it is a significant issue when you're tuning your camera or generating corrections. Any source, regardless if it is shielded or not, can be the cause of high background radiation. Excessive radiation is extremely problematic when you're doing any form of imaging work on a camera. So before doing any work on the system, it's good practice to do a background radiation survey using the detectors. One item of note is you should never use a Geiger counter to check for background radiation. A Geiger counter is a crude radiation device and will not be sensitive enough to accurately determine the background issues. Peak shift issues can have many causes, such as unstable power, temperature fluctuations, and faulty or drifting components. A shifting peak can result in poor image quality. You should always check and adjust the center line and width of your peak before setting up to acquire a flood. Be sure to not only verify the center line of your peak, but also pay close attention to the shape of the Compton and the peak. Sometimes the shape of the peak or the amount of Compton can help direct you to the source of an imaging problem. When running a QA check, whether daily or weekly, verify your uniformity numbers are within OEM specifications or meet the expectations of your nuke med technologist. OEM specifications are important, but you should always do a visual inspection of the flood to check for artifacts. One method of checking the linearity of the camera is to perform a bar phantom image. The bars should be straight and visible in the first 3 quadrants of the phantom, and you should be able to discern bar direction in the 4th quadrant. Most importantly, you should compare these images with previous QA images to make sure no sudden change has occurred. A sudden change of the image can indicate the start or presence of imaging issue. We are looking for consistent images. So you're probably asking yourself, what about my specific camera? What are the usual problems on the cameras that I service? So let's take a look at some specific camera failures, starting with the Forte. The main power for most common components in the Forte camera is derived from the 48-volt power supply. This supply provides power to most of the gantry motions and the imaging electronics. If you suspected of having a problem, check not only the 48-volt DC level, but also check the AC ripple using a DVM. The Detector power supply is a custom-built supply that provides the analog and digital voltage needed by the Detector electronics. This supply is fed with 48 volts from the gantry, which are then broken down into the desired voltages for the Detector electronics. The analog voltages created are individually adjustable, and you should note it is critical that these analog voltages are adjusted and stable to 3 decimal points. The digital voltages are much more forgiving and have only one adjustment that adjusts all 3 digital voltage outputs. The PA-TGB, which is short for preamp trigger board, is the front-end analog board that amplifies the current signal from the tubes to a usable level for digitization. It uses the analog supply voltages, and those voltages must be extremely stable at the components on the board. The DEP, which stands for Digital Event Processor, along with single board computer, provide event sampling and the intelligence to interpret the incoming pulses. It makes on-the-fly spatial position calculations, baseline stabilization, tube gain adjustments, and energy determinations. Some of this information is sent back to the PA-TGB for lifetime imaging control. Some of the information is sent on taxi lines to the acquisition computer electronics. So the primary areas for failure on the Forte gantry motions are the following. The ring limit, rotate limit board is an integral part of the ring lock assembly and closely tied with all transition limit boards. The ring rotate limit board determines physical 0 degrees for Detector rotate, watches for hardware limits in Detector rotate, controls the transition lock motor when moving from cardiac 90 to general 180 positions or vice versa, and oversees motion and limits when executing a gantry roll transition. The collision board detects and holds status information concerning collisions or other unsafe conditions. Once the offending collision has been remedied, the user will need to reset the collision using the motion override button on the gantry display. There are collision sensor pads placed on the Detector bonnets, radius hardware, front slide lock, and the gantry bore surfaces to protect from potential injury when gantry and table movements are taking place. It is possible to bypass the various sensors or pads for troubleshooting purposes, but they can never be left bypassed when a patient is to be scanned. These sensors are also common failure components. The hand controller is one of the most abused parts of a camera. It is often dropped or the cable is pulled beyond its limits, resulting in faulty strain relief and ultimately broken cables. The mechanically actuated buttons also can wear out from constant use. The CAN bus motor controllers are position independent and can be swapped among positions as long as you ensure proper programming. The CAN bus controller is a proprietary 3-axis motion controller that is also capable of driving logic signals for relays, interfaces to motor brakes, and collimator ID determination. Moving on to the next camera, the Skylight is a gantry-free system produced by Philips from 2002 through about 2007. The detectors are attached to the main gantry with a bridge and trolley system, and they use custom servo amps to move the X, Y, and Z motions. The digital servo amps come in 2 variations, 15 amp and 60 amp. The 60 amp version is used for vertical motion. The 15 amp versions are used for all other motions. They communicate via the CAN bus and are dip switch addressable based upon their location. The CAN bus path is a serial daisy chain path. This knowledge can help in diagnosis of where a break in communication has occurred. The table control box provides motor control for both of the telemags of the Sky table. It is a sealed unit and was not designed as end-user serviceable. It's important to understand the controller that was chosen was designed for light-duty use. Therefore, if you're testing the table or controller and cycle of motion in excess of 10% duty cycle, you run the risk of damaging the controller. The theta motors are located inside the detector arm. It is the motor that pivots the detector. The vertical motor located on top of the head arm assembly. It is the motor responsible for lifting the detector, collimator, and yoke. The motors have an encoder permanently attached to the motor. It is indexed specifically to that motor's configuration and should not be messed with. If the encoder or the motor get damaged, both will need to be replaced as one unit. The Skylight hand control is a rechargeable infrared handheld remote control that in normal operation can move all of the available motions. Since there is no attached cable, it is often accidentally dropped, which results in broken casings and erratic problems. Also, when the internal rechargeable battery assembly gets old, it'll lose sensitivity and eventually all functionality. The hand control has a programmable ID, which ensures communication with only the desired Skylight camera. The skid board is the primary interface with the digital servo amps. It provides power to the motors as well as doing power distribution. The Philips CardioMD is a small footprint camera and probably the most successful cardiac camera on the market with over 1,600 units installed. Like all systems, the hand controller is a common failure item and takes a lot of abuse. The acquisition PC communicates with the camera via FireWire. Motion and imaging communication uses this path. The FireWire connection can take a lot of abuse, and its abuse will cause intermittent communication issues that will be reported as FireWire communication errors. The Event Digitization and Correction Board, or EDC, is the intelligent core of the detectors. Communication from the acquisition PC to the EDC is done through the FireWire chain. The EDC controls high voltage, reads diagnostic information from the detector power supply, converts FireWire communication to CAN bus communication for interfacing with 2-axis motor controllers. It controls the DACs for the detector tune, application of corrections, and is responsible for collisions and collimator ID. The 2-axis motor controllers receive motion information from the EDC, providing movement direction and speed information for motions. It controls the motion amp, which drives the stepper motors on each of the motions. It also watches the encoder pulses from the absolute encoders to ensure the motion is moving properly. Motor motion amp drives the stepper motor. There's one motion amp for the vertical or Y motion and one for the detector rotate. The Vertex is a dual ring gantry produced by Philips from 1994 to about 2004 and includes several variations. Once again, the hand controller is one of the most common failure items. The gantry MPU, or the brain, is located in the right-hand rear door of the gantry. It controls and monitors all gantry motions and is commanded by the hand control or the acquisition PC. The gantry MPU stores its mechanical position calibrations in a battery-backed RAM. When the battery degrades enough, the result will be the loss of calibrations when power is cycled. You can check the condition of the battery by measuring across CR2. You should get at least 3 volts. Less than this, and the gantry MPU may lose its calibrations. Calibrations can be backed up to the acquisition PC via a diagnostic utility and should be done anytime motion calibrations are changed. The motor controllers are located on the left-hand rear door of the gantry. Motions are initiated using enable, direction, and velocity signals. The motor controllers output a pulsed DC voltage, which can be measured with a DVM at the motor controller or the motor itself. There are 2 main variants of motor controllers, a 120 volt AC version for radius, table motions, and translate, and a 204 volt AC version for gantry rotate. There are unique adjustments for each controller that affect maximum speed, current load compensation, and acceleration. When replacing a controller, make sure the new controller settings match the old controller settings. Power supply failure is common in all systems. The Vertex has at least 8 power supplies, which include an analog plus and minus 5 volt supply for each detector. The plus and minus 5 volt supplies feed the PATGB and are very susceptible to extremely small voltage fluctuations. The gantry display provides digital LED output of gantry positional information as well as a VFD, or vacuum fluorescent display, which is used for informational and menu structure display. The gantry display assembly is sensitive to the plus 5 volt DC level supplied to the gantry MPU. The Siemens eCam is a very successful general purpose camera made from 1998 through about 2009. There are several versions of the eCam with many different types of detectors. The Detector OEM power supply is the main power supply for the detector head. It provides 5, 12, and 20 volts that power the boards and circuitry and is converted to even higher voltage for energizing photomultiplier tubes that detect the radioactivity. The 5 volt circuit provides power to boards outside of the detector tub that assists with image quality and provides serial connectivity between the detectors and the SNAC, which is the computer that controls the camera. The 12 volt circuit is also used in a similar manner, except it is powering much larger boards, with one located inside the detector tub. The 20 volt circuit is converted to 100 and 200 volts that directly power the tubes. To measure and adjust power output, there are several test points located on the specific boards for each voltage. These are measured with a digital voltmeter and then are adjusted to the ranges specified by Siemens. These are typically very small with less than a 0.2 volt correction margin. The OEM detector power supply is the heart of the detector. If not working properly or at all, can seize detector functionality. The PI59 board is located inside the eCam detector tub and applies uniformity and image resolution during acquisition. This board is the most sophisticated of any on the eCam and is most important when it comes to patient imaging and overall image quality. If the PI-59 is working improperly, it can display images incorrectly, causing erroneous readings and potentially incorrect diagnosis of patients. Because of its location in the detector tub, directly above the high voltage distribution board, it is subjected to constant high temperatures and an extremely static environment. Regular preventive maintenance, daily, weekly, and monthly checks, and proper care will ensure this board performs to the high image standards for which the ECAM is known. Light rails are the patient detection devices which use beams of infrared light transmitted between each rail to maintain a safe distance from the patients during scans and detect possible collisions with the head. Although simple in design, having no moving parts, they function around the C-frame, which is constantly opening and closing. Because of this, the cables that power the rail and communicate with the camera will wear over time. They often take accidental abuse because they are in such a close proximity to the patients, tables, and collimators, which can and will come into contact with the rail. Without functioning light rails, non-circular scans cannot be performed. This includes cardiac, tomo, and whole body scans. The C-frame motor assembly drives the C-shaped frame that holds the collimators to the detector head in and out for exchanges. Even though it only has one purpose, if the assembly malfunctions, it can cause a myriad of issues, from simple collimator ID errors to completely stopping the camera from allowing any motion at all. Constant use, dirt and dust buildup, and general neglect are a few of the reasons this part is so often replaced. It requires grease for quiet and hassle-free operation, but this can attract dust and particulates as well. This buildup of dirt over time causes the motor to become noisy, work harder, and settle between gears, which allows slips and improper calibration. The motor location makes cleaning difficult without taking it out of the system completely. Thus, it is often left with minimal attention and only gets attention when it needs replacing and the camera is completely down. Let's move on to the GE products. The GE Infinia components to keep in mind are the 3-axis motor controller, the crossbar PSD, the SEM board, and the tuba driver. The 200-volt 3-axis controller controls the radial in and out for head 1 and head 2, lateral motion when the system is configured in L mode, and table up and down motion. The 55-volt 3-axis controller controls the swivel for head 1 and 2 and the table linear in and out. If you encounter a motion error, the likely cause may be a bad motor driver that has failed. If a particular motion does not move or gives an error immediately while going through the homing sequence, it could be a failed motor driver controller. Before replacing the motor driver corresponding to the axis that will not move, it is recommended that you issue a GS load command while logged in under service account. This will download new code to the SEM board and initiate a homing and calibration sequence from scratch. If the problem persists, you can check the outputs of the problematic motor driver. If there is no voltage present, then replace the motor driver. For the crossbar PSD panel, if you receive the error driver's voltage test error number 72, etc., it is likely the PSD panel has a failed safety pressure switch and will need to be replaced. Before replacing the PSD panel, check fuse F2 on the SEM board. If the fuse is good, then remove the PSD panel and measure the resistance between the 2-wire connection of the PSD panel to verify safety switches are working properly. The SEM board interfaces with many portions of the entire system. It is the main pathway for communications throughout the Infinia system. It manages the system motion control with the Fox POP board. The SEM board is responsible for getting the detector data to the acquisition computer. It communicates with the CIB or camera interface board in the acquisition computer in order to operate the Infinia system automatically using the GUI commands from the operator. The SEM board receives data from the RCU, or hand control, and also drives the data display. The SEM board can be tested with the system diagnostics to ensure proper function. The tuba, or in some cases the saxophone driver amplifier, is the controller for the gantry rotate motion. If there is no rotate motion or an error is present relating to the gantry rotate while the system is initializing all axes, then it is possible that the tuba saxophone driver has failed. It is recommended to check the dip switch bank SW3 on the SEM board to verify they are correct. If they are correct for your type of Infinia, then issue a GS load command from the service user account. The body contour transmitter and receiver are located on head 1 and mounted on the crossbar. The transmitter and receiver allow the system to scan as closely to the patient as possible by means of radius in and out motion of the detectors. Occasionally, the transmitter or receiver will malfunction and give an error. Contour test failed after all axes have initialized. Check that no objects are blocking the individual transmitters or receivers. Verify that switches on the SEM board, and if the debug program fails, then the transmitter or receiver assembly will need to be replaced. Our last camera is the GE Millennium MG. There are 3 common failure components on the MG. The first is the A1 power supply. The A1 power supply is located in the IPS, which is behind the gantry, and provides power for motion control, detectors, limit switches, and fans. The A1 power supply is temperature sensitive, so airflow is very important to maximize its life. Extreme temperature will damage the components and cause image or peak drift and loss of counts. In a normal functioning state, there are 5 red LEDs toward the middle left of the board that should be lit. The hand controller, or HHC, is connected to the gantry through an RJ45 jack. There are 2 RJ45 jacks on the bottom of each side of the gantry. There are also RJ45 jacks on the patient table and 1 in the back of the IPS. Any one of these jacks can be used, but only 1 controller can be plugged in at any given time. After initially plugging the hand controller cable into the jack, it'll have a faint red LED that blinks 3 times. This indicates normal startup sequence. The purpose of the IN, or the EDI board, is to convert the analog position and energy signals coming from the detector into digital data and transfer these to the PC acquisition console. The IN board is located in the detector. It receives uncorrected raw event signals from the detector, which arrive at the analog block via the J4 input connector. 5 analog signals are received from the detector: energy, X plus and X minus coordinates, Y plus and Y minus coordinates. For troubleshooting purposes, the GENIAC has diagnostics that can be run by logging into the service account and choosing the diagnostic user interface option. You can also swap EDI or IN boards from one detector to another for troubleshooting purposes. However, calibrations may be required if you permanently swap these boards. All of the cameras I mentioned in this presentation are well designed and very successful cameras, and they withstood the test of time. However, like all electronics, they can fail due to overheating, constant use, old age, wear and tear, and abuse. It's important to maintain your camera regularly. It needs to be kept clean and free of dust, proper lubrication, and kept in a good environment. When parts are needed, it's important to source good, reliable parts. And that brings us to the benefits of using qualified reconditioned parts. The biggest benefit of reconditioned parts is lower cost of acquisition, usually 40 to 60% versus new. It extends the life of your system, so no end of life or end of service worries. It provides peace of mind that the part will function when received and will last well into the future. So let's look at qualified reconditioned parts versus as-is parts. Qualified reconditioned part is fully tested in a working system by field-proven and experienced engineers. A certain amount of technical support should be provided with the part. If you're unsure of how to install the part or need help with a calibration after installation, a helping hand should only be a phone call away. No worries about DOA parts, additional downtime, or waiting for a second or third replacement because of the DOA. With an as-is part, you may get a warranty, but a qualified part should include, at the very least, a 30-day warranty. To give you an idea, let's talk about the universal reconditioned parts. Universal reconditioned parts go through a rigorous testing procedure that includes a visual inspection, replacement of obvious failures such as broken connectors, wires, and burnt components. It is then thoroughly tested and are repaired in a working system before final packaging and sealing. All of our parts are stored in a climate-controlled environment and carry a full 180-day warranty. So to summarize, end of life is not the end of the world. With proper planning, training, maintenance, and a trustworthy partner, you can keep your camera operating well beyond the end of OEM life. I hope you're able to gather some helpful information from this webinar. Please take some time to fill out the survey provided, and we will now open it up for any questions you may have for our technical panel.
Thank you very much, Craig. Fantastic presentation. We do have a universal panel of experts with Mike Hill, Chad Watson, and Kevin Bohr to join Craig. The first question here, guys, is what does it really mean when an OEM declares my system EOL?
Okay, I'll take this one, I guess, although I'm not one of the panel of the experts. But, and keep in mind, end of life from each OEM may be slightly different, but, it basically means the same thing. So there would be no roadmap to future upgrades, for example. There's really no engineering support. It's basically a dead-end product. As far as support in the field, they would probably, as I said, provide a best effort maintenance plan, whether that's a time and materials or a full service contract. It just depends on the type of system and, of course, the OEM we're talking about. New software may not be compatible, probably will not be compatible because, as I said, there would be no roadmap to future upgrades. So I hope that clarifies things a little bit.
Okay, moving on to the next one. What should be on my list of daily and weekly quality checks?
Daily, you should check your peak to ensure that it's in the right operating range, and do a daily flood that's extrinsically with like a cobalt sheet source, and check your uniformity numbers to make sure they're in the proper specs. Weekly, you could do a bar phantom check, and a intrinsic uniformity check.
Okay, great. Next one. What can I do to preemptively fix common failures that may cause major downtime?
Well, in there you should keep up on your PMs, your preventative maintenance, keep your environment controlled, your temperature controlled, keep the system clean from dust and debris, make sure it's greased and lubricated properly, and keep your fans running to control the environment that your camera's in.
Okay, got another one here. Do some of the parts mentioned require a specialist to install them, or can I do it myself?
It really all depends on the parts that you're trying to put in. In some cases, the parts do require a significant level of expertise or specialized phantoms or hardware to do the job properly. But most parts are installable by biomed level type people. Some things are even installable by somebody with just a screwdriver.
Okay, got another one here. How do I know when I should stop buying replacement parts and just get a brand new system?
And that's a very good question. It's just like I would compare it to when do you finally trade in your car and buy something new. It's a tough decision to make, and you have to ask yourself, how much are you spending to keep your camera running? But you also need to look at what is your patient load. Are you doing 2, 5, or 10 patients a day? The important thing is to plan ahead and budget for a new camera down the road. UMRI, of course, we have the tools to help you make this decision, but once again, it should probably be based on those two factors. How much are you spending on the camera, and what is your patient load? For example, if you're only doing 2 patients a day, a new camera may not make sense. If you're doing 5 or 10 patients a day, it could easily pay for itself.
All right, looks like we got one specifically for Mike. Is there a general technical training center for biomeds other than the manufacturer?
We have there are a number of the ISOs do provide training. At Universal Medical, we do provide training. We have a training facility or room that is dedicated just to that. We have an upcoming class that's coming in, and we're putting in the particular brand of camera that we're going to be doing training on. It has the classroom and the lab environment all included into one location.
Thanks, Mike. Is there a quick sidebar to that? Is there can they go to your website to get the training calendar for that?
Yes. Yeah, the website should contain all the training documentation, and it should also contain links to the training coordinator, which would be, you'd be able to just email the training coordinator to get upcoming information that might not be published.
Great, great. And again, attendees, that's going to be visit www.uni-med.com, unit-med.com. Okay, well, it looks like it was the last question. Just want to thank Craig and the panel of experts once again for sponsoring today Universal Medical Resources. One lucky attendee will win lunch for their whole department. Details are included in the post-webinar survey, which will appear on your screen shortly. You must complete the survey to obtain your certificate of attendance. And if you do not see the survey, email us at webinar@mdpublishing.com. Thanks again to Craig and the panel of experts and Universal Medical Resources. We will see you next time on a TechNation Webinar Wednesday. Thank you, everyone.
Thank you.
Thank you.